talk to you today about skill learning, as many of us will be, I'm sure. And I'd like to focus on de novo or novel learning. So to get just our intuitions going a little bit here, I'd like to start with an example. This is a keyboard. And the first time you saw a keyboard, you're faced with an arbitrary mapping between your actions, for instance, pressing down on your index finger, and the outcome, in this case, the letter F appearing on the screen. Learning this arbitrary mapping took you some time on the scale of months to years. And when you were first doing this, you had to consider every action as you went through. So for example, if I wanted to type the word cat, I might have to type out C, think of the action, press it down, and then A, think of the action, press it down, etc. Now I can just think to myself, I would like to type cat, and then my fingers just do the work for me. I don't have to go into each action individually. I'd like to go ahead and say that this is an essential component of skill. Once you have a skill, you shouldn't have to worry about individual actions, individual muscle contractions, finger presses. You should be able to just focus on the outcome and have the rest work for you. The other aspect of skill is something that we're all very familiar with, I'm sure, which is adaptation. And the motor field as a whole has done a lot of work looking at how movement skills can be adapted. This makes a lot of sense because most of the learning that we do in everyday life is adaptation. I don't learn not to stub my toe on the stairs by relearning how to walk. And so adaptation in the keyboard can be something as simple as I don't want to have to completely relearn when I move to my desktop keyboard to my laptop keyboard. Or a more extreme example is I don't want to completely start over when I use like an ergonomic keyboard such as this one. The mapping between my action, pressing my index finger, and getting the outcome F is the same. I have to use some adaptation to change how wide my fingers are, exactly the relationship between how far I need to reach to get to a key, but I don't need to completely relearn. And like I said, we know a lot about adaptation. What we know less about is de novo or completely new learning. So let's take the example of the Dvorak keyboard. Now, the Dvorak keyboard breaks the action outcome mapping that you have. So when I press my index finger here, I don't get the letter F, I get the letter U. So I'm going to have to start over almost completely when I'm trying to learn this, which is why you'll never catch me trying to learn to use a Dvorak keyboard. So of course, people have studied de novo learning before, and I don't have time to go into all of these great methods as I would like to. However, I would like to touch on the highlights in order to acknowledge some of our inspiration here. So as you just saw, Giacomo talk about, we have sequence learning. This is a picture, or this figure is from a paper, a 2018 paper out of Digitsen's lab. And sequences are great for teaching us something about habituation as well as other really interesting findings. Unfortunately, it's difficult to know what the underlying mapping is here. It's difficult to define and difficult to manipulate, in my view. We get the same kind of problem with stimulus response mappings. There's this great article from Haith's lab, also 2018 paper talking about habituation with these arbitrary stimulus response mapping. Like sequence learning, you're learning something de novo here, but the underlying mapping is difficult to manipulate. Data gloves are super cool. This is a figure from a Mr. Valde paper from 2005. And here we do get a really clear underlying mapping. That is when you point your finger like shotgun style, you move your cursor to a specific part of the screen. This mapping is really cool. And then there's one more, and this is the one that I adapted for use in my studies. This was this grid sailing task is what they called it. Furman Yoshida, Ito, Yoshimoto, and Doya in 2010 first described this task, which I adapted to create this way. So the important thing here is that there's completely arbitrary mapping between the keys that you press and the direction that you move. So you can see here that the directions are non-cardinal, they're on the diagonals. You don't get all of the directions, you have to learn which directions you can go to. And it's unintuitive. So A doesn't take me to the left, A takes me down and to the right. Okay, so what do we want to know here? I would like to see if we can push people from learning this task through the sequence. That is pressing A, S, S, D, A, right? Push them out of learning that into learning the underlying mapping. The underlying mapping being A moves me down and to the left, S moves me down and to the right. And I am going to manipulate this just by giving one group of participants some information. So I'm going to tell one group, this is the sequence of buttons you need to press. I don't tell them anything about the underlying mapping. I don't tell them what's going to happen when they press those buttons. However, they see the information anyway. So I tell this group, press the buttons A, S, S, D, A. So they are essentially given the cheat code to solve the game. The other group, we don't give this information. So they just are going to hunt around until they get to the solution. Okay, so in the data here, I'm going to show you first across training on the x-axis in the left figure here. And the y-axis is just how well they're doing, a metric of performance, with higher being better. So here we can see that the group that I didn't give any hints to, they show your basic learning curve, nothing particularly special there. And then as you might expect, if I give you the answer, if I give you the cheat code, you are going to learn much faster, and also performance stays very flat. And then on the right figure, you can see that those last 5 training trials are essentially identical. Those 2 groups get to the same place at the end. Okay, none of that is particularly surprising or all that interesting. What we really want to know is about the underlying mapping. And so, of course, one way to figure out if they know what's happening underneath the sequence is to just give a transfer test. So here I'm just going to start moving the start and end locations. So instead of doing the same start and end location that they were trained in, I don't think I mentioned that. My apologies. So all of the participants trained at the same start and end location the whole time they were in training. So this pattern was the only pattern they needed to see, the only pattern that they knew. Then we can move the start and end location to get a transfer trial. Okay, so somewhere in that transfer test, I drop in one trained location. This just gets us an idea of if there's a block effect. We see a very small block effect, but it's equal across both groups. And then the interesting thing is when we go to those transfer locations, we see that there is a large detriment to being given the sequence. So what this is suggesting is that when not given the sequence, the participants are learning something extra. They're learning the underlying mapping between their action and the outcome. Whereas if they're given the sequence, they basically don't bother to do that. And we think that that is a indication that there's an additional computational cost to learning an underlying mapping. One really cool thing about this task, and one of the reasons that I chose it, is that it lends itself really well to modeling under reinforcement learning systems. So one thing that could be happening is that the group given a sequence is learning in an entirely model-free way. So they're just learning that in a state 2, I am rewarded if I press action A, right? And then the group not given the instruction is learning a model-based action. So they're learning the actual underlying mapping. Okay, so let me just quickly run you through how these models work. Model free is going to say, okay, I'm in this space. At first, I'm going to pick randomly. I don't know anything about the action outcomes. So in this case, I pick S. S takes me down and to the right. This is good for me. It gets me closer to the target. So I get rewarded. Next, I randomly pick D. D moves me up. That's farther away from the target. So that incurs a punishment. And then as we move along, we start to assign values for each key at each location. So in the past, I've been rewarded for pressing the A key. So I'm more likely to press the A key. In this space, I've been rewarded for pressing the D key. So in this space, I'm more likely to press the D key, and so on. The model-based model, on the other hand, is trying to learn the mapping, right? So it wants to know what A does, regardless of the position that you are on the board. Okay, so let's start at the beginning. Let's say I don't know anything about what A does. I just make a random decision about where I want to go. Here I'm going to say I want to go down. I decide to press A. A, of course, takes me down and to the left. And that gives me evidence that A takes you down and to the left. And then I can use that information to roll out my desired outcomes prospectively instead of using retroactive information. So for example, what I'm going to do is I'm going to say, okay, if I was to move to the left here, it would take me 3 trials or 3 button presses to get to the ending. If I moved down and to the left, it would take me 2 button presses to get to the ending. I can then map out for every space around me what the best way to go is, make a decision, and press the button most likely to get me there. Okay, so model-based and model-free are 2 competing models. They can also work in concert. There's no reason that you can't have both a simple reward system running under the the model-based system. So we're also going to have a hybrid model, which just applies weights to the model-free and model-based systems. Okay, now we're just going to take a look at what model fits the data best. In order to do that, I need to tell you a little something more about the behavioral data, which I didn't before. So in the leftmost column here, in the leftmost column here, you see that trained location. That's the same start end. But in the transfer, we actually have 3 different conditions of transfer. So you can have the start stay the same and the ending be different. The start change and the end stay the same, or both the start and end change. This is important because the models actually make different predictions depending on which of these transfer conditions you're in. And here's the data for the group given the sequence. As you can see, they're most impaired where the start stays the same and the end is different. And I'm going to start by showing you the model-free version of this, which makes this very clear prediction that anytime the end is what's changing, you'll get a decrease in performance. This is because when you're building those Q values, those values that tell you what action is best in which space, they can still be useful if the end stays the same. Because as you get closer to the end, your action values will start to lead you in the right direction again. If the end is different, then no matter where you are, your action values are going to be wrong. Okay, the next model here is the model-based version of this, which just says you have the underlying mapping. It shouldn't matter where the start and end are. you should know what button to press no matter where you are. And the hybrid model hangs out right in between these. So what you see is that now the hybrid model is following this data best across both, as you might expect, because it's combining the two. But in the no instruction group, it's pulling much more from the model base, and you can see this in the weights. And in the model free, where the sequence is given, the hybrid is pulling much more from the model free version. Okay, so that was a little something about learning de novo and what systems are kind of underlying that de novo learning. Now I want to talk to you a little bit about adaptation. And so I told you before that adaptation is something that I consider to be a very strong hallmark of learned behavior. So in order for us to say that this behavior has been learned, we need to be able to show some adaptation. So I'm gonna, as a proof of concept, I'm gonna roll through just using a mapping that I know everybody has learned. Just arrow keys going in the direction that you would expect them to. And I'm actually gonna use a de novo mapping as a control here. This is just a randomized version of those keys. And then I'm gonna use two adaptation conditions. One is a shifted learning. So here, every key outcome is shifted one finger counterclockwise. Clockwise. So whatever up did, now right does, et cetera, et cetera. And then we have a rotation condition, as you might expect, where all of the outcomes are rotated 45 degrees. And first I'm going to show you that randomized de novo condition. This is our control here. We start with a baseline. The baseline is the direct maps, up goes up, down goes down, etc. We get the training here, and we can see that there's a big drop in performance and then a slow rise. And then here I have the shift condition. You can see that there's a marked advantage to the shift over the random, and the rotation shows an even greater advantage here. And then at the end, we did a little what you might call a washout phase, and we do start to see the hints of an after effect in rotation, which might be interesting for later investigation. We also have started doing this with fully de novo mappings. So here you can see a 6-key version of this where people are trained on a completely novel, arbitrary mapping. And then we have the same shifted condition, and then as a control, random. And I'm just gonna jump through this real quick because I know I'm short on time. You can see there's not much to look at in the time course. But when we go to those transfer trials, you can really start to see that the shifted condition, even though this is a totally arbitrary mapping, the shifted condition is at an advantage over the random. You'll notice that there's no rotation here. It was in the works when the university shut down, so hopefully we'll get to that pretty soon here. So some real quick conclusions. Arbitrary tasks can be learned in at least 2 ways. Through the acquisition of the sequence, just the actions that need to be learned, proceeding almost habitually, and then also by learning the underlying mapping. You can adapt skills that are learned de novo. Adaptation is in fact a very general process. This is something that we have thought for a long time. And that just having an underlying learned action outcome mapping to manipulate is required for adaptation.